Magnetic field acts on any moving charge, whether it is a single charge or whether it is a stream of charges. Like here, we have a stream of charges coming from this battery into this wire. A stream of charges means electric current. So the magnetic field between the north and south poles here will act on this stream of charges by a magnetic force. When you apply the right-hand rule, you can predict the direction of the magnetic force depending on the direction of the current. It can be going this way or that way. With this polarity, this is the positive lead of the battery. So current is going this way, the motion is this way, V is this way, field is this way. When you apply the right-hand rule and the four fingers here will curl toward the field which is going downward, then the force will be going this way. The force will be going this way. So you need to apply the right-hand rule in order to predict what happens to a current carrying wire. So here we have this magnetic field into the screen. If the current is 0, the wire will be straight. Once you apply the current in one direction, you apply the right-hand rule, the force will be going this way to the east. And because of that, the cable, the wire will bend this way. If you reverse the current, then the magnetic force will reverse and the wire, the cable, will bulge in this direction. In general, any current is a stream of charges, as we see here. So we can examine the action of the magnetic field on the current by going into the details of the electric current. We have the drift velocity here, and inside the conductor, each charge moving with VD, drift velocity V, in a field which is directed into the screen. Each such charge will have a force. The direction of the thumb, when you apply the right-hand rule, assign the four fingers to the direction of V and curl them into the screen toward the direction of B. The thumb will point upward. That would be the direction of the magnetic force. Since the angle between V and B is 90 degrees, the force will be maximum. So it is a QVB sine 90, which is just 1. Now, the volume is equal to the cross-section area A multiplied by L. The charge density, number of charges per unit volume, is N, charge carriers, which is for copper wires 10 to the power 28 electrons per cubic meter. So the number of carriers is NAL. Each one a charge Q moving with velocity VD in a field B. So this will be the net force. So now we recall what we learned before, that I equals NQVAD. We substitute here for NQVA. We substitute the value I. So the maximum force is equal to BIL. So the magnetic force on a single charge is QVB, but on a current carrying wire is BIL, where I is the current and L is the length of the wire. If the angle is not 90 degrees, so we have to take sine theta into consideration. So in that case, the force is BIL sine theta. BIL sine theta. The maximum force occurs when theta is 90 degrees and sine 90 degrees is 1. So you need to apply the right-hand rule. you assign the four fingers to the direction of motion as usual, which is the direction of I. You curl the four fingers toward B. The thumb of your right hand, in this case, will point out of the screen. That would be the direction of the magnetic force on this wire. Many applications are built around this concept, the action of the magnetic field on a current carrying wire. For example, loudspeakers, we have a coil. The current representing the sound will be sent through the coil, and the field, we have here a permanent inside the cone of the loudspeaker. The field lines will interact with the current, and as a result, the force, if the current is going this way, the force will be in this direction, so this cone will move this way. Usually the cone is attached to an elastic diaphragm. It can move in and out. If the current is reversed, then the force will be reversed. So the current representing the sound signal will be going in both directions, therefore the force will be in both directions, in and out. As a result, when the cone oscillates in and out, the pressure applied to air molecules will be going from compression to refraction waves, and this way the loudspeaker generates sound waves, mechanical sound waves, converts electrical signals representing sound or audio signals into sound waves that can hear. This is another application of the magnetic force. In some critical applications, like the pump for artificial hearts or the pump for kidney dialysis machines, we cannot use ordinary pumps because ordinary mechanical pumps can damage the blood cells. So this is one idea where we make use of the magnetic force that acts on the ions. As we know, the blood is made of charged ions, positive ions. That is usually the case. And wherever you have charges in motion, blood in motion, or urine, or any liquid in a human body, there are ions. These ions, as they move, they create currents. So the magnetic field acts on these currents and induces a force which will move them in one direction according to the right-hand rule. If the current reverses, then V reverses. So this way we can create a pump that will act push and pull depending on the direction of the current, and allows for the separation of the ions.